Welcome to the lecture 26 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. This is the first class of 6th week. In this week, we will mainly focus on electrical modeling of solar photovoltaic cell. In last week, we have covered different solar cell structures, including bulk crystalline silicon solar cell, thin film solar cell, organic solar cell, nanostructured solar cells, and also we have discussed the technological evolution behind this structure modification. In this lecture, we will focus on electrical modeling for solar photovoltaic cell. And first we will describe the modeling of PN junction under dark condition, considering the continuity equation, the drift diffusion model, and we will derive the current in a diode under dark condition. Say PN junction under dark condition, if we apply some bias, say forward bias, we have some current, we know the expression of current, but the derivation of current and the assumptions behind this derivation is important. Why? Because you know, when a PN junction solar cell is illuminated and an external load is connected in the solar cell, then due to photocurrent flow through the external resistance, there will be a potential drop across the external resistance. And this potential drop will be in such a direction that it make the forward biasing of PN junction. So if you remember, we have described the working principle of solar cell. Then basically this was a PN junction. Suppose this is a PN junction under illumination. If we connect external load, so photocurrent is flowing from left to right in this figure, and the potential drop across this will be like this. So this will forward bias the PN junction, excess hole is flowing from inside quasi-neutral region to the boundary of the depletion region in the inside, and then they cross the junction and they reach ultimately at the boundary of the depletion layer in the P side. And to maintain the charge balance, electrons from external circuit will flow in this direction. Is electron flow. So current is opposite direction, the photocurrent direction will be like this, and in this direction from the external circuit some holes will be flowing. This production of voltage, or this voltage across the resistance, external resistance R, this will make the forward biasing of PN junction. So current expression for PN junction under a forward bias condition is important to obtain the total current expression or the modeling of solar photovoltaic cell. So first we will derive the expression of current called diode current or current in the dark condition when the PN junction diode is forward biased. So let us consider the P side is biased more positively with respect to the N side. That is nothing but forward biasing of the PN junction. Now if we neglect the resistance of quasi-neutral part of the PN junction diode, we can assume that the applied bias, applied potential in the P and N terminals will appear across the depletion region. So total voltage what is applying, say Vf is the forward bias voltage is applied. So that will be appearing across the depletion layer only. Quasi-neutral part is no resistive, this is a fully conducting. This assumption we are taking, say. Due to application of this bias, Fermi level will not be aligned. Due to application of bias, Fermi level will no more be aligned now. And the splitting of Fermi level into two different Fermi levels called quasi-Fermi levels, that is EFP in the P side and EFN in the N side, and the difference between these Fermi level, the gap between these quasi-Fermi levels will be nothing but Q times the applied voltage, Q into Vf. This band diagram also we have discussed in some earlier classes. Now height of the potential barrier will be also reduced due to the presence of forward bias voltage. And the amount of this reduction of the barrier height, that will be by Q times Vf. Vf here is the forward bias voltage compared to the barrier height at equilibrium. Barrier height at equilibrium is nothing but Q times Vbi, Q times built-in potential. And now the barrier height will be Q times Vbi minus Vf. And this results the diffusion of carriers, for example, diffusion of holes, majority holes from P side to N side, and diffusion of electrons, majority electrons from N side to P side. This will be extra diffusion than in case of equilibrium, because in equilibrium also we have seen in the establishment of equilibrium there are diffusion of holes from P side to N side and electrons from N side to P side. But this diffusion will be additional diffusion due to reduction of barrier, potential barrier. This we can call injection of carriers. That means holes are injected from P side to N side and electrons are injected from N side to P side. But after injection, that is when these holes from P side reaches to the N side, they become minority, because in N side holes are minority carrier. So in N side already present holes, that was the minority equilibrium hole, that will be increased. Similarly, in the P side, injected electrons from N side will be minority, and this minority will add to the minority at equilibrium. That means due to application of forward bias, there will be a injection of carriers, holes from P side to N side, and electrons from n side to p side, and ultimately they will create some excess minority carriers in both the side. Now important is how the carrier distribution after application of bias. If we see the figure, you see N0, this is the equilibrium value of majority carrier concentration in n side. It is much greater than Pn0, which is minority holes in n side at equilibrium. But after injection, due to presence of extra electrons, the minority carrier profile will be like this. This is shown here. This will be the minority carrier profile. At the junction, near the junction, at the boundary of the depletion layer, it is highest and it gradually decreases with position. We will show you this expression of this curve is nothing but some constant into e to the power minus x by Lp. So there is an exponential decay. Similarly, if we plot the excess minority in the p side, there is electrons, this is denoted by delta n. This also decreases exponentially with position, and ultimately at a long distance from the junction, it matches with the equilibrium value Np0. For simplicity of calculation, we are assuming the depletion layer width is very small and the position of x is equal to 0 is at this junction, that is starting of boundary, that is boundary of the depletion layer at in the N region and depletion boundary in the p region. But in right hand side this is positive x and in negative this side it is minus x. Say this is x dash, another axis system, there is x dash, which is nothing, x dash is nothing but minus x. Why this is? And this is also exponentially decay, and if you observe the expression, there is delta n into delta np, there is a some constant value here, maximum value, e to the power minus x dash by ln. X dash by ln, it decreases, but if you put the x dash value, this will be minus x. So minus x dash means minus minus plus x, but this plus x, but in the p region, x is itself minus value. That means say any point here, this is say minus 2, this is say minus 3. That means ultimately this will be e to the power minus some value divided by ln. So ultimately it decreases, but the axis system is x dash is taken for calculation. The shaded region shows the volume of or area under this shaded region, gives you the total extra minority holes coming in the inside, and this also shaded region indicates the area under this curve, indicates the total excess minority electrons which have been injected from n side to p side due to application of forward bias. Now, if we like to calculate the continuity equation, because this is required to derive the expression for the current, and continuity equation gives you the total balance equation, and along with this you have to also use the current density equation, that we have derived the approximated photocurrent expression in some earlier classes. So say continuity equation for holes in inside we like to write first. Again, if we refer to the figure, the same figure, Due to presence of concentration gradient of excess minority holes in n side and excess minority electrons in p side, these excess minority holes in n side will starts diffusing from left to right. So these holes will diffuse from left to right due to concentration gradient. So diffusion occurs in this direction. Here also diffusion occurs from right to left. Diffusion of electrons here. So from this concept you can have a idea about the direction of current. Since the holes are diffused from left to right, so direction of current will be also from this position to this direction. That is from left to right in the inside, and which is nothing but the current direction. And electrons are diffusing from right to left, so movement of electron is opposite to the direction of current. So that's why current is again from here to here. That means left to right in the p side. So ultimately the current flow within the device will be look like this. This is the current flow due to electron diffusion, and this is the current flow. This inside is hole diffusion, and this is the current flow due to electron diffusion, J direction. So but electron diffusion is left to right, and this is the current expression IN. This is a hole, so current is also in this direction, IP. This is IP. So ultimately current in the same direction. Say, coming back to the continuity equation, we can write the continuity equation for, say, holes in the inside first. This holes in the inside. So at any position here, if we write, so rate of change of extra holes, that is Pn minus Pn0. Say Pn is denoted as the concentration of holes after injection, and Pn0 is the equilibrium value. So what is the excess value? This is the extra value, Pn minus Pn0. That will be 1 by q Jpx minus Jpx plus delta x by delta x plus some generation Gp rate, if any generation is there, minus recombination part. Recombination of holes depends on tau p, and this is extra holes divided by tau p. This is the formula we have assumed. The recombination rate is nothing but extra amount of carriers divided by the average lifetime. As we discussed earlier also, this continuity gives you the total balance. Now, if we consider the diode, the generation rate will be nothing, because this is under dark condition we are now discussing. So if you consider the Jpx minus Jpx plus delta x by delta x, if we consider the limit delta x tends to 0, so this will become nothing but the derivative. And also you remember Jpx minus Jpx plus delta x by delta x, this is itself a negative value because of decrement nature of the conduction current. So for the limit delta x tends to 0, we can write left hand side del t of Pn minus Pn0. Let us express this Pn minus Pn0 in terms of delta P. Delta P is the excess minority holes. Here we have mentioned, say. So this equation becomes del t of delta P is equal to 1 by q into minus del Jp del x in the limit of delta x 0, and also this is negative because this Jx minus Jp x plus delta x, because with increasing x from left to right, it reduces this value. That's why minus sign is appearing. So the Jp Jx is itself negative. Now, as we mentioned, the dark condition Gp is 0. So let us put this is 0. And if you put this 0, so equation will be modified. And at the same time, say at steady state, rate of change with time del delta t of delta p will be 0. So considering the steady state and generation rate is 0, we can write the equation number 31. This is from 31 we have derived. So let us write this equation in this way. So del t of delta p is equal to minus 1 by q del Jp del x minus delta p by tau. We say this is equation number 56. This formation of equation is important. Now we have to put the value of Jp, this conduction current. Here we have to apply the drift diffusion model. What is the drift diffusion model? Means carrier may flow, that is carrier may create the conduction current due to flow by drift and by diffusion. If there is both electric field present and concentration gradient also present, then the component Jp will come from component drift component and also diffusion component. So that the current density expression, that is the expression or the relation of this Jp with the other parameters, will be used to simplify. Let us see. Anyway, so for electron also we can get the similar expression. Suppose this expression is 57 and delta n is nothing but Np minus Np0. That means I want to mean excess electrons in the p side, that is the left side, Np minus equilibrium value Np0. So if considering steady state, we reach the equation, this expression 56 and 57. What is the current density equation that we were discussing? Say for holes, current component due to holes, Jp. This is the drift part and this is the diffusion part. Similarly, the current density equation for electrons will be, this is some drift part and diffusion part. If you minutely observe, this is nothing but sigma into E, the current due to drift. The drift electric field is required. That's why the presence of electric field is here. And in diffusion current, this depends on the diffusivity or diffusion coefficient, dP, ddx of delta p. That is a concentration change, how the concentration of delta p is varying with multiplication of dP and Q. This gives you the diffusion current. So this is called drift diffusion model. This is drift, this is diffusion part. And for electrons, this same expression, some sigma E plus diffusion component. But be careful, the sign of diffusion component here minus and this is plus. Why? The holes due to drift flows in the direction of electric field, and diffusion of holes take place from higher concentration to lower concentration. That means ddx of delta p is itself negative. So this negative and this negative will be combined to give the positive, and then diffusion of holes from say left to right in the direction of electric field, and drift of holes from left to right due to electric field, say a direction of electric field from left to right, and diffusion also in the higher to lower, the same direction. Current will basically added, current will be added. So this plus ultimately it will be coming plus. No, actually you don't think this minus this. So net current will be additive for drift plus diffusion component. Same direction is flow. Similarly, Here also drift part and diffusion part will be added. Plus sign is there. But remember, electron flows opposite to the electric field. So one negative will be coming here. Similarly, this due to slope negative, this on negative, another negative will be coming here. So negative, negative, ultimately they are in the same direction. They also additive. The direction of this current will be negative due to Jn, and if you put the value of q electron again, it becomes positive, but in case of holes this is positive charge, so this remains positive itself. So this both negative and then again it will become positive q due to q value. So ultimately Jn and Jp will be in the same direction. This also you be careful. In any device, the current Jp and Jn in the same direction. Okay, let us proceed. This already I mentioned. This is x dash is a axis for excess electrons in p side we will be considering. Now, in case of flow of excess holes or excess electrons in the quasi-neutral region, there is no electric field present. If there is no electric field, so obviously the drift component will be vanishing for both the cases. Now, Jp will become Jp is equal to minus q dp ddx of delta p, and put this Jp value into the continuity equation 56. You will get at steady state left side 0 is minus 1 by q ddx of minus q dp ddx of delta p. Just I have put the value of Jp in the equation number 56. Just earlier we have discussed. Minus delta p by tau p, which gives del d square dx square delta p is equal to delta p by dp tau p. Also for electrons we can get. Ultimately this gives you Lp square, because this dp tau p product is nothing but Lp square diffusion length, already discussed some earlier classes. This is called minority hole diffusion length in the n side. Similarly, if the expression of Jn, that is if you remove the drift part, this will become q dn ddx of delta n, that you put here in the 57 and you consider the steady state. The left hand side will be 0 and 1 by q del x of Jn. Jn means again q times dn ddx of delta n, q cancel out, and d square dx square delta n will be coming. Another term, that is delta n by tau n, this will be present, but dn is associated with this term, but we have changed it to the another term just like this. So we get d square dx square delta n is equal to delta n by ln square. This is the equation for minority electrons in p side. We have assumed in the quasi-neutral region there is no electric field, no potential drop. That's why only diffusion exists. Now solution. What is the solution? This is the differential equation of second order. This is the form d square y dx square is equal to y by some constant or ky. D square y dx square is equal to k into y. So the general form of this expression is some constant exponential x by Lp plus some constant exponential minus x by Lp. This constant Lp, this root over this Lp whole square. So this term is coming Lp here. And in the solution, if you observe, this x is positive here. So in the figure, if you go from left to right, if you move from left to right, that means x is increasing. If x is increasing, we are observing that delta p decreasing as per the physics. But this equation, first term, tells that with increasing x, it should be increasing. It is not possible. Say at x is equal to infinity, it becomes infinity. It is never possible based on the physics. So a must be 0. So solution reduces to b exponential minus x by Lp. And now boundary condition is required for finding out the B value. What is the boundary condition? If we see the expression again, in this case, x is equal to 0 position, this value of delta p is maximum. What is this delta p? Delta p means this value minus in Pn 0. Now what is this value? This is an important to find out this value. How can we calculate this value? It is shown here. Let me just first write down this value at the x is equal to 0. The x's whole is nothing but Pn 0 plus delta Pn. And delta Pn, which is the value of x's minority holes at the boundary, you can write this value is delta Pn. Delta Pn will be P at xn, if we put this value xn, minus Pn0, the Pn0 value. So Pn0 exponential Vf by Vt minus 1, this is equal to how? How it is coming? Because P at xn, this value is nothing but Pn0 exponential Vf by Vt. So Pn0 will be taken out as a common, this will become. But how we will get this P at xn, that is xn means this position boundary of the depletion layer at the in the n side. For this relationship P at xn and n at minus xp, we have to follow some expression. What is that? Let us start from this basic equation, that is pp0 by pn0. What is this pp0 by pn0? pp0 by pn0 indicates that pp0 is the majority hole concentration in the p side by minority hole concentration in n side. The relationship between this pp0 and pn0, they are governed by a equation that is exponential vbi by vt. This is very important. Majority carrier in other side will be related to the minority carrier in other side, the opposite side, by this expression, the built-in potential, exponential, because my majority is greater than this minority here. How much greater? This is greater by exponential built-in potential by Vt amount from the whole concentration in other side, this side. Similarly, the Nn0 value, this value will be greater than electron concentration in other side by an amount exponential Vbi by Vt at equilibrium. Be careful. What happened under forward bias? If the forward bias is Vf is applied, so barrier height will be reduced by amount Vf. So Vbi minus Vf, the relationship holds same way, but only the exponential Vbi minus Vf term will be coming. Vbi minus Vf by Vt. So the majority and minority in other side, they are related by now this expression, or majority here and minority here are related by this relationship. Now P at minus xp, what is the value of P at minus xp? This is nothing but pp0. pp0 is nothing but the majority carrier concentration, and P at xn value, P at xn is nothing but Pn0 in case of equilibrium value. So this will be, can be written exponential Vbi minus Vf by Vt is equal to pp0, P at minus xp is pp0 by P at xn. Now assuming P at minus xp is equal to pp0, that is Na, and n at xn value is n0 and nd, we can write again, say P at xn, what is the value of P at xn? This is our intention, to find out the P at xn position, that is this position. That is minority x's holes at x is equal to 0 from this graph, or x is equal to xn value here. So P at xn by Pn0 can be written as Pxn by Pp0 into Pp0 by Pn0, that is by dividing this factor into multiplication by this factor. This will be Pxn by Pp0 and Pp0 by Pn0. Already we have got the expression. What is this expression? That is Pp0 by Pn0 is equal to exponential Vbi minus Vf by Vt. So put the value of Pp0 by Pn0 here. This is the value. So just Pp0 by Pn0 will be exponential. So Pn0 by Pp0 will be different. Minus Vbi minus Vf by Kt. And this Pp0 by Pn0 exponential Vbi by Vt. So Pxn by P from this expression, yes, you see this is the value of Pp0 by Pxn. That means Pxn by P, this indicates P at xn value, that is x's holes in the xn boundary divided by Pp0, that will be exponential is equal to minus Vbi minus Vf by Kt, and this value is used here. So this value is nothing but this, and this value Pp0 by so finally we get exponential Vf by Vt. P at xn, that is this value, x's minority whole at xn is equal to Pn0 into exponential Vf by Vt. That's why we have written Pxn is equal to Pn0 exponential Vf by Vt. Putting this value, we can have a delta Pn. Delta Pn value at x is equal to 0. This boundary condition you have to put in the equation to find out the constant B. Similarly, we can obtain n at minus xp, that is x's minority electrons at minus xp will be np0 exponential Vf by Vt. Or for remembering, you can remember in this way that this x's minority holes here is related to the Pn0 value into exponential sum extra value Vf by Vt. That means this extra injection due to forward bias. Again you repeat this Pxn, or here also P at xn value, that is x's minority whole at xn is equal to equilibrium minority in that side, the same side, into exponential Vf by Vt. This amount is increased. So the plus value indicates it is Pxn is more than Pn0. The same thing. Similarly, Np value here will be greater than Np0 by factor Np0 into e to the power Vf by Vt. If you increase the forward bias voltage, this height will be increasing. But we have considered low level injection, that means the excess minority holes concentration is much less than majority carrier concentration. Suppose majority carrier concentration is in the order of 10 to the power 17 per centimeter cube, and equilibrium minority concentration say 10 to the power 6 per centimeter cube. After injection, it may reach to the 10 to the power 10, 10 to the power 11 per centimeter cube, but which is still less than the majority carrier, that is 10 to the power 17 per centimeter cube say. So the solution of this equation ultimately you can get by putting the value of B, delta Pn exponential minus x by Lp, which is delta Pn value is nothing but Pxn minus Pn0, which is Pn0 exponential Vf by Vt. I told you that the exponential decay, you see this coming from the solution. This is exponential decay. Some constant delta Pn, this is delta Pn extra at x is equal to 0 or x is equal to xn position into exponential minus x by Lp. The equation number 60, that is important. Similarly, for minority electrons in p side, taking x dash is equal to minus x and considering the x axis system in x dash axis system, you can get delta np exponential minus x dash by ln, also decay. Now diffusion current. So this current is diode current is mainly due to diffusion of holes and electrons. So diffusion current, again you have to use the expression to find out the net current in the diode. So diffusion current expression IP due to diffusion is QA dP, because the continuity equation we have expressed in terms of J, that is current density, but for making it current we have to multiply with the junction area A just. So IPX, that is coming from JP, is minus Q dP ddx of delta Px only multiplied by A, so IP. If you put the value of this delta Px from the solution whatever we have obtained, you will get this the expression QA dP by LP delta Pn e to the power minus x by Lp, which is nothing but again the expression of delta Px. So you can write here it is a delta Px, right back. This is nothing but delta Px. Also, the current due to electron diffusion will be In x dash, will be this, and this diffusion current you have to take at the boundary, that is x is equal to 0. So this is the maximum, this is the diffusion, the slope is maximum. So In x dash will be like this. So this is the minus sign here is coming, but the sign convention already I discussed why this is minus. Ix dash is x dash equal minus x. So ultimately this current, the direction of this current will be contributing or will be adding to the current due to holes in the same direction. The current will be in the left to right in case of this example, from left to right side. So this will be added. So you can take the just mod of this. So at x is equal to 0, if you calculate the current IP, this will be due to hole, because diffusion current at x is equal to 0 is taken due to the maximum slope, maximum change in the gradient here. This will be the expression for the diffusion current component due to hole. And earlier, whatever we derived, this is the position dependent current, IPX, but we have not got the value of IP. IPX, this is a position dependent. Here also position dependent value, but to get this value, we have to put the x is equal to 0. So this is the current where the slope is maximum, the change is there. So this is IP. Similarly, the electron current will be QA dN by ln NP0 exponential. This a similar form of expression only with a sign negative. And the discussion regarding the flow of current already I discussed. So this current will be added to the whole current ultimately by putting the value x dash minus x, ultimately you get plus. So total diode current ID will be IP at x is equal to 0 plus IN at x dash is equal to 0, or modulus of this, because is minus sign is coming, and the logic behind this taking minus plus sign is already discussed. The term which is common in both the exponential term is the common to both. So you have to take exponential common, exponential Vf by Vt minus 1, and the rest part, that is Q times A, this dP by Lp Pn0 plus dN by ln Np0. This whole equation, whole expression is called reverse saturation current, because dimension of this will be also a current in ampere if you follow. So ultimately the diode current expression is expressed in a very well known form, that is ID is equal to I0 exponential Vf by Vt minus 1. This expression is the ID. This is expression number 66. This is very important. People used to utilize this expression everywhere. So in a diode current expression, that is under dark condition, if forward bias is given, that will be the diode current. So under illuminated condition, when photocurrent is flowing across the external resistance, the voltage drop will be also behaving as a forward bias to the diode. So the dark current component will be in the same expression. and in that case Vf, that bias voltage will be the V load, because voltage across the load in case of the solar cell expressions. So Vf will be V load if it is illuminated in case of, suppose this is PN junction, under illumination, external resistance is there, R diffusion length, anyway. So VL will be appearing in the expression of the solar cell equivalent circuit model or equivalent model. So VL will be appearing in the expression for dark current in the model equation for solar cell. One important note, we have assumed there is no recombination during the derivation of the expression. If you consider the recombination at the junction due to interface, additional term eta, which is called ideality factor, sometimes it is represented as n also, or n also by n. Eta or n. Sometimes it is denoted by n also. The expression will be I0 exponential Vf by eta into Vt minus 1. Eta stands for the recombination at the junction, and for silicon diode, eta value is equal to 2 generally. So this is more practical model equation for the diode considering the ideality factor. So we have derived the expression for current in a PN junction diode under forward bias, which can be used in the model equation for solar cell to write the dark current component. We have derived diffusion equation from continuity equation and current density equation. Then we have shown in detail how they could be solved. Finally, we reached to the diode current expression based on some assumptions and boundary conditions. These are the references you can follow for this derivation. Thank you.